Are functions that are representable as power series around some point, okay? We can define them as analytic at one point, also on a set. If it is going to be analytic on a set, then we must show that it is going to be representable as a power series at all points of that set. For instance, if you take this function, 1 minus set, okay? I'm claiming that this is analytic on a set of whole complex numbers except the point 1. Or if you want to look at this as a real function, 1 divided by 1 minus x, you can also say that it's going to be analytic on r minus 1. Okay? How can we show this? First of all, I'm claiming that around the point 0, this function is representable as a power series. Why? Around 0, we have this, right? Z to the power of n. N from 0 to infinity for all those z's such that their modulus is less than 1. Or if you are looking at this as a real function, 1 divided by 1 minus x is this sum of x to the power of n for the values of x such that their absolute value is less than 1. Okay, so I have been able to find a radius r. Here it is 1, such that around point 0, I have this disk, and it is going to be represented as a power series. Look at this. This is the point that is not working for us, and this is the point that I'm trying to write that representation. Inside of this, we can represent this function, but if we go a little bit further to this point that our function is not defined, then we are not going to be able to write it. This is around point 0. But my claim is that it is not only analytic at the point 0, but it is analytic for all other points which are not 1. How can I do this? This trick is very useful for us, and you need to be aware of using this trick. We are making a shift half like this. Assume that we are taking sum a, which is not equal to 1. Okay? I want to write a power series expansion for this function around the point a. This is my function, right? If you write this as, if I want to have a power series expansion around a, what was the terms? Some coefficients times z minus a to the power of n, right? So I need to see that z minus a. How can I do it? If you write something like this. Is it true? Minus z plus a, yes. This is the same thing, right? Take a factor out of 1 minus a. Can we write this as 1 minus a times 1 minus z minus a divided by 1 minus a? Can I do this or not? You see, if you take this 1 minus a, multiply it here. 1 minus a multiplied by 1 is this one, minus 1 minus a multiplied by this one is z minus a. Okay, so they're exactly the same thing. Since this a is also not equal to 0, this is something meaningful, right? It is 1 divided by 1 minus something which is not 1. So it is not equal to 0, so we have it. Now look at this. 1 divided by 1 minus something. Is it something similar to what we know? Yes. And we can write a power series expansion for this. Then when the absolute value of this one or the modulus of this one is less than 1, right? So this is going to be equal to 1 divided by 1 minus a times n from 0 till infinity of z minus a divided by 1 minus a to the power of n. For all of those z's such that this z minus a, 1 minus a is less than 1. Equivalently, we can write this as 1 minus a. Okay? I can also turn this into the standard form of power series, which is going to be one minus a to the power of n plus 1. I have 1 minus a to the power of n from here, and 1 minus a from here. If you multiply this, this is going to be power to the power of n. Okay? What is the meaning of this? This is valid for all z's such that their distance from a is less than the one's distance from a. Okay? If you have a point A, for instance here, okay? What is the distance of A from the point 1? It is this one, right? For all z's that their distance is less than this distance, which is going to be actually this circle. Okay? I haven't been able to draw a good circle. It is much more like an oval, but anyhow. For all of these values, this is valid, right? This is a very important fact to remember. When we are looking for this interval of convergence or the disk of convergence, and we are trying to find out what is happening to this radius of convergence, when we look at it at the complex plane, we can easily spot that radius. If this is my point, we need to just calculate the distance of that point from the points that our function, this generating function for the power series, or one of its derivatives is not defined. Here this function is not defined at point 1. So which means that if I'm starting from this point, I can make this bigger and bigger and bigger and bigger until I hit the point that the function is not defined. And this thing is going to give me the radius of convergence. If I was going to, for instance, expand this function as power series around the point -2, I think. Let's say -2, okay? Then what would have been our radius of convergence? Again, around this 2, we can start extending these things until we hit the point that our function is not defined. And what's the distance between -2 and the point that this is not defined? 3. So the radius was going to be 3. If I was looking at the point I, and I want to expand this as a series around the point I, then what would have been our distance? If this is my I, this is my point 1, which is, my function is not defined here, and I want to expand this function as a power series around this point I. What would have been my radius of convergence? We have again this circles, until we hit this point, and we cannot expand it more, right? So it's going to be this distance, right? And what is that distance? Yes, square root of 2. Square root of 2. You see, looking at this kind of things in the complex plane directly gives us what is the radius of convergence. Okay? This is a very fundamental example. Please don't forget about this. Don't forget about this series expansion, and also the method that we use to, expand it around some other points. Okay, another example. If you have a polynomial, f of z as, I don't know, a0 plus a1 z, directly a1 z. plus a2z2 up until ak z to the power of k. Okay? Is this function an analytic function or not? First of all, I need to say that around which point it is analytic. What I'm claiming is that any polynomial is analytic on the whole complex plane. Why? First of all, around the point 0, can I write this as a power series? It is already written, right? A0, A1, and the rest of the coefficients are going to be 0. What is the radius of convergence for that power series? This is defined where? This is valid for which values of z? For which values of z? Or even if you're working in the real line, okay? For which real number I can plug here and I get again a real number? For all of them, right? For all of them. For any real number that you can plug here in the z, the result is going to be a real number, right? So it is actually a convergent power series for all of the real numbers. Not only for all of the real numbers, but also for all of the complex numbers. Okay? So the radius of this is infinity. Okay. What this shows, that this is analytic around the point 0. We are claiming that this is an analytic function on the whole complex plane. So if I take another point, can we also extend this around that point? Can we have a power series expansion around that point? How can we have? Again, with this idea of shifting, right? If you write this z as z minus a plus a, let's say, okay? What will happen to the powers of this? It will be this one, right? It is going to be this one to the power of n plus the rest. And if here, instead of z, you write these things, okay? This will turn into f of z equal to a0 prime plus a1 prime times z minus a up until ak prime z minus a to the power of k. Okay? And again, this is a power series representation around the point a. Okay? This a0 prime, maybe it is going to be a0 plus this a that is coming from here, and from here, and from here, and from here. So there's a lot of numbers, but you're putting them under one umbrella. This is also maybe going to be much more things based on this a's and a0s and a1 and so on. And we're gathering all together, and so it is clear what is happening. So this is also another analytic function. What about another example? This function 1 plus z to the power of t. Do we have a power series representation for this function around the point 0? We have written it, right? Go back, check it. In the 1 divided by 1 minus z, or 1 minus x, we plug minus x to the power of 2, right? So around the point 0, it is analytic. Show that it is analytic on the set of all complex numbers minus plus minus I. Okay? Or if you are working on the set of real numbers, this is an analytic function on the set of all real numbers. How can we show this? We know a power series expansion around the point 0. But it does not mean that this is analytic on the whole of the complex plane. We need to also have this representation around all other points, which are not I or minus I. Okay? How can we do this? If I give you a hint, we can write this 1 plus z to the power of 2 as this or the partial fraction decomposition of it, okay? You need to find this A, you need to find this B, and some kind of taking a factor out of minus I or I, you will turn this into 1 divided by 1 minus Z, something like that, okay? And if you write that power series expansions, you will see that around the point, or any point that you can again add anything, you will see that this thing is going to be as summation of two power series, which will give you it as a what? Analytic function. If we have this power series for this function around the point 0, okay? What is the radius of its convergence? From here, it is not very evident that what is this radius. We need to go write that series, then I don't know, try to find that ratio and so on and so on and so on, like we did before. But if you look at the complex plane, I is here, minus I here, right? And we're expanding, for instance, this around which point? Let's say 0. At this point, my function is not defined. At this point, my function is not defined. If I start expanding around this, circles or this neighborhoods, how much I can extend this? I can extend this till I get to this point or this point. Or the points that my function or one of its derivatives is not defined. And what is that point? Either I or minus I. So I can extend this circle up until this point. What is the radius of this circle? 1. The radius is 1, right? Which means that the radius of convergence of 1 divided by 1 plus z to the power of 2, if you expand it around the point 0, is going to be 1. If you expand it around this point, what will happen? We will again start looking for circles, okay? Till we hit this point. Not here, this function is not defined. So the radius is going to be this much. Okay? This power series, Cn x minus a to the power of n. When I'm writing x, I'm working with the v variables. Is convergent for all x's such that their distance from A is less than r. Or on this interval of conversion, this is a convergent power series. Okay? Let me call this f of x. Okay, n from 0 to the infinity of Cn x minus a to the power of n. Okay. What can I say about this function being analytic or not? In the examples before, we started with simple functions that we know that they have a power series representation, and we showed that they are analytic. What is happening here is this. I'm starting with a convergent power series, or I'm taking a power series, and I know that on some interval, it is convergent, so this is meaningful. This is a function. On this interval, I can plug values for x and get numbers. My question is this. Is this an analytic function or not? First of all, around the point A, can you represent this function as a power series expansion or not? Yes, we can do it, right? Since we can do it, it is analytic at point A. Okay? But is this enough for me to call that this function is analytic on this whole interval? I don't know. Yes? I need to some kind of show that on other points on this interval, this function also is representable as a power series. At first it seems that I again use this trick, right? Instead of writing x, if I want to expand around the point C, I write x as x minus c plus c. Okay? Or if I have this x minus a, instead of x minus a, write this. Okay? Now, if we replace this instead of this x minus c and c minus a to the power of n, like what we have done for a normal polynomial, okay? It seems that we are shifting the center of this power series representation from the point A to the point C, to another center. Okay? But question, when we are doing this, we are going to have infinitely many terms. Are we sure that this is going to be a valid power series? Are we sure that it is going to be convergent over there? Why this function is analytic on the interval? This is not that easy to show it just by changing the center. But it is true. As a research question, okay, you can work on this. Why, if you have a power series, then it is going to be an analytic function. But this is actually true. We can also change its center, and again we can represent this as a power series. Okay? For this kind of functions, we have three important things that you need to know. First is that if you have this kind of a function, f is infinitely many times differentiable. F is many times differentiable. And if you want to calculate, for instance, its derivative, f prime of x, how do we do it? If I have this object, which is Cn x minus a to the power of n, okay, and I'm trying to take its derivative, how can we do it? The thing is that when we are having power series, and if they are convergent on some interval, their derivative also exists on the same interval. I'm not sure about the boundary values. Here for x equal to a minus r and a plus r. Okay? For the boundary values I don't know, but I am sure that inside this interval, this function is differentiable. And if you want to calculate its derivative, you can do it term by term, which means that you can just calculate derivative of each one of these terms. And what is the derivative of each one of these terms? The Cn is just a constant, remains here. X minus a to the power of n's derivative. N times x minus a to the power of, so it is going to be n times Cn x minus a to the power of n minus 1. Okay? If n starts from 0, this is going to be 0 times this thing, okay, which is going to be 0. So we normally start with this 1. Okay? So, a power series can be differentiated on its interval of convergence term by term. Is it true that for other kind of series we can do this term by term differentiation? Absolutely no. One example. Look at this function, f of x equal to sine of n factorial x divided by n to the power of 2. Okay? This series is an absolutely convergent series, right? Because if you calculate the absolute value of this is going to be less than 1. So it is going to be smaller than or equal to 1 divided by n to the power of 2. And we know that it is a convergent series, which means that this is something meaningful for all of the values of x's. Okay, this is a valid function. But if I want to calculate its term by term derivative, or if I want to calculate the derivative of this function, if I do it term by term, which means that if I calculate derivative of n factorial times x divided by n to the power of 2, this is going to be what? This n factorial is going to come out. Okay, it is going to be n factorial divided by n to the power of 2 cosine of n factorial x. Okay? And if you look at this as a function, it does not exist at all. Because n factorial times cosine or whatsoever, this is not going to be a convergent series. This is a divergent series. Check that out. Use that things that you know to check that if this is a convergent series or a divergent series. And you will see that actually it is not. Which means that we can only do term by term differentiation only for power series. And where we can do it? Only on their interval of convergence. Again, this is itself a power series, right? What is its interval of convergence? It is again the same interval of convergence as the function f itself. Okay? If you want to calculate the derivative of this one, what will you do? Again, differentiate term by term. This is going to be L, n minus 1, c n x minus a to the power of n minus 2, and so on and so on and so on. Okay? Another thing is that f is integrable and to the infinity of c n x minus a to the power of n plus 1 divided by n plus 1. Okay? This means that if you have a power series, okay, and it is convergent on this interval of conversion, then if you want to calculate integral of that function, you can calculate that integral by integrating each one of these terms of the series. Okay? And this thing itself is again a power series which is going to be convergent, and its interval of convergence is again going to be the same thing. Okay? What about the endpoints? The endpoint of this interval on the left hand and the right? We can say nothing. Its behavior can change. It can be both convergent, it can be both divergent. We can say nothing about it. We need to check for each one of these cases. Okay? I'm not writing it, but again the same thing is true here. If you want to integrate a power series, then you integrate it term by term. Another thing is that if this f of x is going to be like this, Cn x minus a to the power of n, this Cn's cannot be any arbitrary number. They are some kind of related to this function f of x. And how they are related to this f of x? Can we find out that? What time write my f of x is? I will come back and write this as Cn equal to something, but How can I write my function f of x? This is c0 plus c1 x minus a plus c2 x minus a to the power of 2, c3 x minus a to the power of 3, etc. Okay? If you want to calculate this value of c0, what is a trick that you can use? Instead of x, which value I can plug? So I can a, right? You have a point. Which one of you was it? Okay? If here, instead of x, we write a, what will this be? This will be f of a. What will happen to the right hand side? This is going to be c0 plus 0, 0, 0, 0, 0. And we're done with it. Now, we have found c0. c0 is some kind of related to this function. And it is the value of function at the point a. What if we want to find c1? What should we do? What can we do in order to some kind of isolate this c1 and plug some number over there to see what's happening? Yes. I have a plus by the way. If we take derivative of f's, okay, differentiate u over dx, what will happen to the left hand side? It's going to be f prime of x. Is f prime of x exists? Are we sure that, do we know that derivative of f exists? Yes, since it's a power series, we have already talked about it. We haven't given proof, but that's a claim that you can prove it by yourselves. And if I want to calculate derivative of this whole thing, how can I proceed? We know that power series can be differentiated term by term, which means that take derivative of this one, take derivative of this one, take derivative of this one, and so on and so on and so on. So what is this derivative going to be? C0 is 0. What's the derivative of this one? C1 plus what's the derivative of this one? 2 times C2 x minus a plus 3 times C3 x minus a to the power of 2 and the rest. Now, what is our C1? How can we get to know the C1? Again, plug a. Yes. If x is a, if x is equal to a, what will happen to the left hand side? This is going to be f prime of a. F prime of a. And what will happen to the right hand side? This is 0, but we have the C1. Again, C1 is some kind of related to the function. Okay? What about C2? If you want to get to know C2, what do you have? Again, take the second derivative. What will happen to it? F double prime of x is going to be what? This goes, we have 2c2 plus 3 times 2 times x minus a plus the rest. Right? And if we again plus x equal to a, what do we get? F double prime at point a is equal to 2 times 1 times C2. Okay, from here, what is our C2 then? Second derivative at point A divided by 2 factorial. Okay? If we do this one more time, what will happen to our C3? What is happening? What is the pattern that is emerging? The derivatives are going upper and upper.
So when we take, let's say we take its derivative,
okay.
See where we want to remove the effect of derivative. So we
yes.
are dividing its power.
Yes.
Power
Yes, exactly. So if you want to give a general formula for Cn, and if you continue this process, you will see that this Cn is going to be the nth derivative at point A divided by n factorial. Okay? Or the Taylor coefficients. We will talk about this. When we are talking about the set Cn of u, this is just a shorthand notification. I'm going to explain what I'm saying. This is going to be the set of n times differentiable functions with continuous nth derivative. Okay? When we are talking about CU, it is the set of continuous functions, only continuous. When we are talking about C1 of U, we are talking about the set of functions that are one-time differentiable with that derivative as a continuous function. When we are talking about C2 of U, we are talking about the functions which are 2 times differentiable and their second derivative is continuous. Okay. What is the relationship between these sets? Is any continuous function differentiable? No. For instance, what about f of x equal to absolute value of x? Is it a continuous function? It is a continuous function. Here take u as r. It's a continuous function. Is it differentiable at all of the points on r? No. It is not differentiable at the point 0. Okay? Which means that not only, it is not true that all continuous functions are differentiable. But if you have a differentiable function, what can you say about its continuity? If a function is differentiable, then it is continuous, right? So what is happening? We have more functions that are continuous than differentiable. This is something like this. What about the relationship between these two sets? What kind of inclusion do we have? We know that 2 times differentiable functions are all 1 time differentiable, right? So it is going to be like this. Is this equality or not equality? Do we have functions which are 1 time differentiable but not 2 times differentiable? We have this kind of functions, right? I can continue like this, and I can write Cn of u here. Now, I need to ask you 2 questions. Maybe they can be research questions for you. Can you give me an example of a function which is n times differentiable, but its n plus 1 derivative does not exist? Can you construct such a function? I give you a number, for instance, 100. Give me a function that is 100 times differentiable, but its 101st derivative does not exist. Also another question. This absolute value of x is a continuous function, but it is not differentiable only at one point. Can you give an example or construct a function which is continuous everywhere, and its derivative does not exist at none of the points? Continuous everywhere, non-differentiable everywhere. What kind of a function is this? Okay, these are 2 side questions. Now, let's continue this chain. If I continue this chain, what will happen? Let me come here. I can continue till C infinity functions. What is C infinity? It is the set of all functions that are infinitely many times differentiable. Okay? Infinitely many times differentiable functions. Is this the end of the story? No, actually we can go one step further. We can talk about C omega of u. Okay? This is the set of all analytic functions. Now, question. Do we have a function which is analytic, but not here, or not here, not here? I cannot say that is there any function that is analytic but not infinitely many times differentiable. My question is this. Like the thing that we are talking, constructing a function that is n times differentiable but not n plus 1 times differentiable. If you have infinitely many times differentiable functions, is it also an analytic function? Which means that is it also representable as a power series? If I have a function which is infinitely many times differentiable, is that function also an analytic function or not? Which means that can I represent that function as a power series? If we are able to represent a function as a power series, what would be its coefficients? The cn's that we have written here, right? The nth derivative at that point divided by n factorial. My question is, I take an f here, okay? Which means that this function is infinitely many times differentiable. Is it true that we can show this f as f of a plus f prime of a x minus a plus f double prime of a divided by x minus a to the power of 2 at a 3 factorial x minus a to the power of t, etc. What I'm writing is actually this: c0 plus c1 x minus a, c2 x minus a to the power of 2, etc. But I know that if I write this like this, then these coefficients must be like this. That's why I'm directly writing it. So my question is this: if I have a power series, which I know it is a convergent, which I know that it's interval, and so on and so on and so on, I know that it is infinitely many times differentiable. And if you want to calculate their derivative, what should we do? Differentiate term by term. Now my question is this: if I get a function that is infinitely many times differentiable, can I represent that function as a power series? And if I can, how I can? If I cannot, how I cannot? And so on and so on. You have something to say, right? Please.
I think we can make it silence. We cannot write.
You say that this is not true, right, for all of the functions.
Yes.
Can you give me an example? Which means that give me an example of a function which is infinitely many times differentiable, but it cannot be represented as a power series, or a power series which is going to look like this. Which, by the way, we call this representation Taylor series representation. I will come to that. What is your example?
My example is sin x.
Sine of x is representable as an infinite function. What? Sine of x is a function which can be represented. We will come to that. But sine is not a good example for a function which is infinitely many times differentiable but not analytic. Take this function. E to the power of minus 1 divided by x to the power of 2 when x is not equal to 0, and 0 when x is equal to 0. Okay? This function has a graph like this. It is very flat there on this point 0. By very flat, what do I mean? I will just tell you. This is 1 and this is our function. You can show that as an exercise. You can show as an exercise such that derivative of this function of any order for all any nth derivative of this function at point 0 is going to be equal to 0. Okay? Now, if I want to represent this function, which is infinitely many times differentiable, okay, as a power series around the point 0, what should I write? I should write f of x as what? F of a. What is f of a? What is f of 0? 0. Plus, what is the coefficient of x minus 0 or x? Derivative at point 0. What is derivative at point 0? 0. You're going to show that. So it's going to 0x. If I want to find the coefficient of x to the power of 2, I want to write second derivative at point 0 divided by 2 factorial. What is second derivative at point 0? 0. So it is again 0x to the power of 2, etc. And this is equal to 0. This is true for our function. Is our function around a point on a neighborhood of 0? Is it completely equal to 0? No, it is not. If around 0 you go a little bit to right or left, this is going to be a positive number. It is not going to be 0. So this is not a power series representation for this function. Which means that although this function is infinitely many times differentiable, it is not an analytic function. Which brings us to this point. This inclusion is also strict. Okay? There are functions that are analytic, but there are functions that are infinitely many times differentiable, but not analytic. So analytic functions are, again, a very special type of functions. Okay? Good? Now, our question which remains is like this. If I take a function which is infinitely many times differentiable, so I can come to this up until here, I can go down up until here. What are the conditions such that I can jump also to this part? What are the conditions that if I impose on some functions, I can say that, okay, they are analytic functions? For instance, we know a few of the functions. 1 divided by 1 minus z, 1 divided by 1 plus z to the power of 2, all of the polynomials, and so on. These are analytic functions. But what about other functions? If you give me some function, can I be sure that it is an analytic function or not? Even if it's infinitely many times differentials exist. In order to be able to answer to this question, we need to use the following. It is called Taylor's theorem. Okay? Assume that f is a real-valued function on this interval. Take a number, okay, a natural number. All of these differentiables are continuous, or fn minus 1 is continuous. What do I mean by this? N minus 1's derivative of f is continuous, which means that f is of class Cn minus 1. Okay? F is of class Cn minus 1. If this n minus 1 derivative existence continues, what we can say about n minus 2 derivative, n minus 3 derivative, or the first derivative, second derivative. What about all derivatives of lower degrees? Since this exists and it is continuous, the functions that were coming in the steps before that, they also exist and they're also continuous. Okay? Continuous and f of n of x exists for all x in AB. Okay? Here I have a function which is n times differentiable. That's all. Okay? Take two distinct numbers. This I called it alpha and beta. Sorry, alpha, beta, A and B, distinct numbers A and B in and define T n of x, let's call it, k from 0 to n minus 1 of fk at point a divided by n factorial x minus a to the power of k. What is happening here? In this summation that we have here, we are only taking n first term of that. Okay? This thing is called the Taylor polynomial. And be such that our function evaluated at point B is going to be equal to value of this function, okay, Tn of B, plus nth derivative at point D divided by n factorial B minus a to the power of n. This works for all of these a and b's inside this interval. Let's look at this. Let's look at this very simply. I have a function f of x, okay? I can represent this as a Taylor polynomial plus some remainder. What is our Taylor polynomial? If you are looking for this function around point A, it's going to be f of A plus f prime of A, x minus A, plus f double prime of A divided by 2 factorial x minus A, up until which one? F n minus 1. At point A, n minus 1 factorial x minus a to the power of n minus 1. Okay? This is the same function here, what we have here, the Taylor polynomial, plus it is going to be written as or represented as nth derivative evaluated at some point t. Here our t lies between a and x. Okay, so I am basing this function, the expansion, around the point A, and this x is some point around A. If I want to see that if I start at this point and I write an expansion locally around this point A, the points that are also around this interval, how can I evaluate the values of this function based on what we are constructing here in this point? Okay. Divided by n factorial x minus a to the power of, okay. What we have here, this one, this whole thing is the Taylor polynomial. Taylor polynomial. And what we have here, this is our remainder thing. The remainder. What is happening here? If we increase this number n, and if we are guaranteed that this function f is infinitely many times differentiable. If it is infinitely many times differentiable, I can continue as I like, right? If it is only 3 times differentiable, I can only continue up until here. Okay? And write the third derivative. If it is 10 times, I can write a Taylor polynomial of degree, which is covering up until 9. And the rest, okay? So, if we take a function, which is infinitely many times differentiable, we can write this Taylor series plus a remainder. If we want a function to be analytic, what did we need? We needed to represent that function as a power series representation, right? And when we are going to have that power series representation for our function, when this Rn of x, when this remainder, when this goes to 0, okay, or this error term that is here, if it's 0, then we can write this f of x as the Taylor series expansion of our function. Which means that, in this case, our function is going to be analytical. What does this mean? In short, if for a function which is infinitely many times differentiable, we look at this and look at this remainder. If this remainder, if this Rn of x goes to function 0 as n tends to positive infinity, okay, then what will happen? This Taylor polynomial will turn into a Taylor series which will represent our function around the point A with nothing as an error. And this means that we have been able to represent our infinitely many times differentiable function as a power series. Which means that what will happen? It will be an analytic function. Good? Now we need to work on some examples. If I give you this function e to the power of x, exponential function, can you write a power series expansion for this function, for instance, around the point 0? First of all, what do we need to look for? We need to be able to know that this function is infinitely many times differentiable, and the remainder here for our Taylor representation, this is going to go to 0. First of all, is e to the power of x an infinitely many times differentiable function? What is the derivative of e to the power of x? So it exists, right? The first derivative is e to the power of x. What is the second derivative of e to the power of x? E to the power of x. So again, the second derivative exists, and what about the third derivative? Fourth derivative, nth derivative, and you can continue this ad infinitum, right? So it is infinitely many times differentiable. I am going to let you to have this as an exercise. You can also read the book. There is the details of this on there. Exercise. Show that for f of x equal to e to the power of x, okay, Rn of x from from Taylor's theorem tends to 0. Tends to 0. Okay? Which means that e to the power of x is a analytic function, right? And since it is an analytic function, it can be represented as a power series expansion. Can you please write a power series expansion for e to the power of x around the point 0? Which means that how can we represent this e to the power of x as this kind of a power series? And from 0 to infinity. Let me turn this again into C, because we have used C for coefficients. C0, C1x, C2x2, C3x3, etc. How can we write this? We have found the relationship between coefficients and the function itself, right? What is the Cn? This Cn is going to be nth derivative of our e to the power of x at point 0 divided by n factorial. What is the nth derivative of e to the power of x? E to the power of x is itself, yes. So it is going to be e to the power of 0 divided by n factorial, which is going to be what? 1 divided by n factorial. Now what does this mean? This means that e to the power of x is going to be equal to, instead of Cn, what should I write? Yes, x to the power of n divided by n factorial. And this is term n from 0. This is a power series around which point? 0. What is the radius of convergence of this? The radius of convergence is positive infinity. What does this mean? It means that this equality holds for all of the real numbers. What does this mean now? We have constructed this function by means of these polynomials around which point? 0. This means that if you go as far as you want around 0, okay? No matter how far you go, to left, to right, or whatsoever, the error term from Taylor's theorem is always going to get to 0 if you continue to adding these terms together. Which means that although power series are local structures, now this is so much powerful that it can be used globally to calculate the values of e to the power of x. Although you have constructed it around the point 0, but no matter which point you go, you can calculate the value of that function at that point around 0 if you add enough terms of this series. What is the value of this at point x equal to 1? X is equal to 1 is a valid point, right? I can give it. If you plug x here as 1, what will happen? This will be e. What will this be? This summation from n from 0 to infinity of 1 divided by n factorials. So this is also another representation for the number e. Okay? This is one of the most important power series representations for functions. In your engineering life, wherever you go, you will use this. So this is a very important thing. You need to know about this. Okay? Good? Instead of using this thing, okay, maybe sometimes you're going to forget about this formula. If you do not want to memorize anything, how can we derive this again? Wherever you want to, again, find out these formulas, there is no need to remember them. You just need to write this, okay? What is the value of the function at point 0 if you want to find out about C0? Instead of x, what should we plug? 0. What is e to the power of 0? If you plug 0 here, what will you get? C0. Got it. If I want to calculate C1, what should I do? Take derivatives, right? What is derivative of e to the power of x? E to the power of x. So e to the power of x is going to be C1 plus 2 times C2x plus 3 times C3 x2, etc. Again, instead of x, if you plug 0, what will you get? This is going to be 1, this is going to be C1. Okay? If you want to get to know C2, what we'll do? Again, take derivative of this. What will happen? It will be e to the power of x equal to 2 times C2 plus 6 times C3x and the rest. If instead of x you write 0, what will you get? 1 equal to 2c, 2c2, and what will be c2 then? 1 divided by 2. 1 divided by 2, and if you continue, you will see that it is getting clear. Good? My second claim. This function sine of x is also an analytic function. Why? Is sine infinity many times differentiable? Yes, it is. But is it analytic? Can we be sure that an infinity many times differentiable function is analytic? We cannot be sure unless we know that the remainder from Taylor's theorem is tending to 0. For sine of x, yes, it is tending to 0. So it means that you can represent sine of x as a power series, for instance, around the point 0. Can you please do it? What is the Taylor series expansion for the function sine of x? What is the first derivative of sine of x? Cosine of x. What is the second derivative of sine of x? Yes, minus sine of x. What is the third derivative? Minus cosine of x. What is the fourth derivative? It's going to be sine. What is the fifth derivative? Since again we are taking the same thing, we are back here to the function itself. It is going to be cosine and we are repeating it, right? Okay. If I want to calculate this C0, what should we do? Calculate the value of the function at point 0. If instead of x we plug 0, what do we get? C0 is 0. C0 is 0. What about C1? We take its derivative, calculated at that point, divided by 1 factor. This is the general formula, right? Cn is going to be n's derivative. Since we are doing it around the point 0, evaluated this and 0 divided by n factorial. Okay? Now, what is C1? First derivative at point 0 divided by 1 factorial. What is first derivative? Cosine of x. What's cosine of x at point 0? Cosine of x. 1, yes. So it is going to be 1 divided by 1 factorial, which is 1. What is our C2? This is going to be second derivative evaluated at point 0. What is second derivative at point 0? Divided by 2 factorial, which is, let me write it also. What is C3? Third derivative evaluated at point 0. It's going to be minus 1 divided by 3 factorial. What is C4? Fourth derivative evaluated at 0, which is going to be 0 divided by 4 factorial. What is C5? Fifth derivative, again we come back to the function itself. Yeah, cosine of x, sorry. Okay? If evaluated at point 0, 1, so it is 1 divided by 5 factorial, etc. So what is happening to our sine of x? Our sine of x is going to be x minus x to the power of 3 factorial, x to the power of 5 factorial, etc. Okay. How do we represent this? It is minus 1 to the power of n, if it is 0, n plus 1, x to the power of 2n plus 1, 2n plus 1. Right? X. This is n. Yeah. Yes, of course, we have this factorial here as well. Thanks. Now, this is a power series, right? Question. What is its radius of convergence? What is its interval of convergence? What should we do? We should again calculate this limit of an plus 1 divided by an, what we have had before, or this coefficients. Let's calculate it. Let's calculate this limit, the radius of convergence, because we know the center. Let's calculate the radius. This is going to be limit of Cn plus 1 divided by Cn, which is going to be limit of, what is our Cn by the way? Minus 1 to the power of n divided by 2n plus 1 factorial. If instead of n, I write n plus 1, what will I get? Minus 1 to the power of n plus 1. And what will this be? 2n plus 2 plus 1. Yes, it is going to be 2n plus 3 factorial. Divided by minus 1 to the power of n, 2n plus 1 factorial. Okay? We can get rid of this minus 1s. This is inside absolute value. This is going to be limit of 2n plus 1 factorial, 2n plus 3 factorial. How can I simplify these? Yes. Yeah? It is inside absolute value. So absolute value of minus 1. You can write this 2n plus 3 factorial as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. This one and this one will cancel. And what we'll have? We will have limit of 1 divided by 2n plus 3 times 2n plus 2. And what is that limit going to be equal to? 0. So our R is going to be what? Past infinity. Around which point we were writing this expansion of power series? Around 0. If around 0, I have a radius of infinity, I can say that this is true for all of the real numbers. For all x in R. I'm writing for all x in R, but you can show that this is actually true for all of the complex numbers as well. Okay? Which means that we can also define, for instance, sine of a complex number. And how do you define it? The sine of a complex number? Using this series. Okay? Good? Fine? Naturally, after this function sine, what is the function that comes to mind? Cosine of x. But can you be clever without going all these things and doing this kind of things? Give me the power series representation of cosine of x. How can you do that? We have said that power series are differentiable functions, right? Are differentiable functions. Okay? And if we want to calculate their derivatives, what should we do? We should take their derivative term by term. No. What is the derivative of sine of x? Cosine of x. If I want to calculate the derivative of this thing, or derivative of this whole thing, what should I do? I should take the derivative one by one, right? Term by term. What is the derivative of this term? Minus 1 to the power of n divided by 2n plus 1 factorial is just a constant, okay? It will remain. What is the derivative of x to the power of 2n plus 1? We will have 2n plus 1 times x to the power of 2n. That 2n plus 1 with this 2n plus 1 factorial, okay? And it is going to be minus 1 to the power of n x to the power of 2n divided by 2n factorial. Right? Or this is going to be 1 minus x to the power of 2 factorial, plus x to the power of 4 factorial, etc. What is the interval of convergence for this series? It was the same as the function that we were taking the derivative, right? Since this is defined for all of these things, for all x in R. Okay? What was the power series expansion of this function? X to the power of n, right? These are the important series that you need to know. And this is true for which values of x? For values of x that are between minus 1 and 1. How did we get it? Here, instead of x, if you write minus x to the power of 2, you will see it, right? So here, instead of in the series, we plug minus x to the power of 2. So it is going to be n from 0 to the infinity of minus 1 to the power of n x to the power of 2n. For which values? When x is between minus 1 and 2. Okay? On the interval of convergence for power series, we said that we can also take integrals, right? By the way, maybe I will give you this as an exercise. Take derivative of both hand sides, by the way. You will see that if you take derivative of these things, you will get to new functions. We will do it. Just let's continue with this, we will come to that. I should not have passed it, but anyhow. We have this, right? And we know that we can take integral of these functions on their interval of convergence and it is going to work. So, if I calculate integral of this one from 0 to x of 1 divided by 1 over t2 dt, this is going to be what? Integral of this whole thing. Integral of this whole thing. If there are some other functions here and they are not power series, be very careful. You cannot just pass the integral inside of the series. Okay? You need to have something which we call uniform convergence of functions. Talking about this is beyond our scope, of course, but you know that and remember that. It is not true that when you are taking an integral and a series, you can just flip there or pass the integral inside of the series. You need to have some uniform convergence, but for power series it is true. If you have a power series, you can pass the integral inside of the series. So what will happen here? We will calculate this n from 0 to infinity of integral of this thing, right? And what was it? We have calculated cn x to the power of n plus 1 divided by n plus 1, which is going to be minus 1 to the power of n x to the power of 2n plus 1 divided by 2n plus 1. Okay? For which values? For between minus 1 and 1. What is this? This integral is equal to arctangent, right? So it is going to be arctangent of t evaluated from 0 to x. So it is going to be arctangent of x minus arctangent of 0, which is 0. So here I can write this as tangent inverse of x. Let me write it as equal to this integral again. Okay? Good? Question, one more thing. When we were talking about taking derivatives or integrals of power series, we said that we are sure that inside this interval of convergence, we have convergence. But what about the endpoints? Can we be sure that for x minus 1 or for x equal to 1, this function is convergent or not? We need to check it. We have this theorem, which is called Abel's theorem. Abel's theorem. When we were talking about this Abelian groups and so on, it is the same guy. Abel and Cain sanırım. Habil, Kabil şeyleri var ya. Aynı adam. Aynı. If f of x is equal to this Cn x to the power of n for x is between minus 1 and 1. Okay? We have this kind of a power series around 0, and we know that it is convergent for minus 1 and 1. Okay? So I can call this a function f. If instead of x, if I plug 1, what will I get? I will get this series, right? If this is convergent, then what will happen to the value of this f? We will have this limit of f of x as x tends to 1 from left, it is equal to the value of this series. Okay? How can we make use of this Abel's theorem? Hangisi? Ne? Söyle. fx. Let's look at this series. What is this? If here instead of x I plug 1, what will I get? I will get to this series, right? Minus 1 to the power of n divided by 2n plus 1, which is going to be what? One minus 1 over 3 plus 1 over 5 minus 1 over 7, right? Is this series a convergent series or not? If we want to study convergence and divergence of a series, what should we do? We have a systematic way to do it, right? Necessary condition, yes. Necessary condition is satisfied. Okay? We need to go to other steps. Is it geometric, P series or alternative? It is alternative series, so we are good to talk about it. What is Leibniz's test? What is here our an? 1 divided by 2n plus 1, right? Is this a decreasing sequence? Yes. Is it a null sequence? Is it tending to? Yes. Which means that by Leibniz's theorem, this is convergent. Okay? Convergent by Leibniz's theorem. Leibniz's test. Now, if I want to know which number this series is going to tend, can I make use of Abel's theorem? Look at this. we had this power series, which is convergent between -1 and 1. And if we place 1 instead of x, again we have a convergent series. So what will be its value? Its value will be limit of f of x when x tends to 1 from left. So this is going to be equal to limit of arctangent, okay, when x tends to 1 from left. What is limit of arctangent when x goes to 1? It is equal to arctangent of 1, right? What is arctangent of 1? I divided by. This is one of the first examples that we see this number pi appears, and it is not defined as, I don't know, the ratio of a circle divided by its diameter. If you want to calculate numerically what is the value of pi, what should you do? What you should do? Add 1, -1 divided by 3, +1 plus 1, -1. Do this many times and then multiply the result by 4. This is giving you a way to numerically calculate what is the value of pi. But interestingly, this is a very slow series, which means that if you want to calculate the values of pi, you need to calculate many different terms, which is not that much good. So we are looking for other ways to calculate the sample, for Ramanujan series and this kind of weird stuff. But anyhow, this is also called the Leibniz series. Okay, keep that in mind as well. I'm letting you to calculate or find the generating function for this series, nx to the power of n, based on this. How can you do this? Or even x to the power of n. Take derivative of both hand sides. You will have n x to the power of n minus 1. Then multiply both hand sides with an x. You will get to this one. Okay. What is the series for 1 divided by 1 plus x? In the series, instead of x, we are plugging minus x, right? So it is going to be minus 1 to the power of n, x to the power of n. Okay? Again, this is true for values of x between minus 1 and 1. Okay? Let's take integral of both hand sides. What is the integral of 1 divided by 1 plus x? It is going to be ln of 1 plus x. Okay, from calculus 1 you know it. What will happen to the right hand side? We know that we can take this integral term by term, which is going to be, this is starting from 0, and from 0 to the infinity of minus 1 to the power of n, x to the power of n plus 1 divided by n plus 1. Okay? Which is true for which values? For values of x which is between minus 1 and 1. Good? Question. What is the behavior of this series at the points x equal to minus 1 and x equal to 1? Is it convergent or divergent when value of x is minus 1? 1 plus minus 1 is the ln of 0. This is even not undefined. What will happen to here if you plug minus 1? It is going to be what? This is going to be harmonic series, right? If you look at it. What about the value of this function at x equal to 1? What about the value of function at x equal to 1? What about the value of the series at x equal to 1. When x is equal to 1, what do we have? Let's again write it here. This is going to be n from 0 to the infinity of minus 1 to the power of n divided by n plus 1. Right? Which is what? 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. Right? Question. Is this a convergent series or a divergent series? Why it is convergent? It is an alternating series. And again, it satisfies the conditions of Leibniz's theorem. So again, by Leibniz's test, it is a convergent. Okay. Can you find out which value is the series going to converge? So what is the summation of 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and so on and so on and so on? Does this satisfy the conditions of Abel's theorem? It satisfies, right? We have this function, which is here. It is convergent for minus 1 and 1. And at the value of 1, when we replace it, here this series, or the series of the coefficients, is convergent. Okay? Which means that this series is going to be equal to as what? If you have this, you can also use this one, right? This is going to be limit of x when x goes to 1 from the left. This is going to be limit of ln of 1 plus x. And what is this limit equal to? ln is a continuous function, right? So we can take this limit inside of it. This is going to be ln of limit of 1 plus x as x goes to 1 from left. And what is that equal to? 1 plus 1, right? Which is 2. So this limit is equal to ln of 2. ln of 2. This limit is 2, but since it passes, so it is going to be ln of 2. Which means that this alternating series is summed up to ln of 2. Fine? Good? Everything's clear? Good. Today we have talked mostly about power series. Power series are super important tool for you. Okay? And what is happening is this. As you see from the Taylor's theorem and what we have done, there are some kind of encoding derivatives of function. Okay? Each coefficient of this x to the power of 2, x to the power of 3, they're encoding some kind of derivatives of the function. If we want to, for instance, encode some other information about function, what should we do? Or why this 1, x to the power of 2, x to the power of 3, and these polynomials of, why they're special for us? Are they really special, or we can also use some other kind of functions? You will see that we can also use some other kind of functions. For instance, we can use sine and cosine. And if you want to expand the function such that it is going to be as an times sine of x plus bn times cosine of x, you're actually writing the Fourier expansion of a function, which is also very important when you're working with a lot of things. You will use them in your engineering life. But the thing is that you need to remember is this. This one, x to the power of 2, x to the power of 3, are not very important things for us. But they have some special properties. Okay? They are orthonormal to each other and this kind of things. Sine and cosine are also the same thing. They can also be used to encode information about the functions and also some other functions as well. In differential equations course, you will see that, okay, this kind of things will really be helpful for you. And also you can use other type of functions, especially if you are working on Sturm-Liouville theories. You will see that you can find out about functions that are very special functions, and in the space of some functions, you can encode information using based on them. Okay? These are way behind our course, but keep in mind that These are some kind of tools to encode information about our functions. Okay?